Do small angle approximation with this group?
Back in
Chapter 6, yes.
Oh, when we were deriving the formula for centripetal motion.
Yep.
If the angle's greater than 1, then sine of the angle is approximately the tangent of it. Which is approximately the angle.
And one correction, if theta is much less than 1.
Much
I think you said greater than 1.
Yeah, yeah, it's much less, yes.
It's the double less
The
than.
double, yeah.
So as long as theta is not too big here, then, so if theta is small, then we were left with, I guess here, negative g theta is equal to L alpha. We now have it in the form that we wanted over here. We have negative of some number times the displacement is equal to some number times the acceleration. We've already done the complex math. Once you accept that that is true, well, now we'll just use some of the stuff we've already done. We got the analogy here. So theta is analogous to displacement, alpha is analogous to acceleration. L, the length of the pendulum, is analogous to the mass, and G with K. My period for simple harmonic motion is 2 pi square root of m over k. My period for a simple pendulum, just transliterate. M and L go together. K and G correspond. And so now I have a formula for the period of a simple pendulum. And we can actually test that and have satisfactory results. And then you will rejoice. And it's not even lab day. Let's take this thing out. All right, I think it's relatively stable. All right, so basically we can swing this thing back and forth. Now notice that the mass of the object really doesn't matter. The mass is not part of the formula. What matters is how long it is, matters that the angle is small, and it matters what the acceleration due to gravity is. Matter of fact, we can use this to calculate the acceleration due to gravity. Now we know it's 9.798, or hopefully you trusted me, 9.798 meters per second squared. So we need to know the length of this. Now the length is going to be from the pivot point to the center of mass. Now this is one area where it deviates from or a nice ideal, the fact that all the mass should be at a point mass at the end. String does have mass, this does have mass, but we assume that this is close enough, and having done this before, it's close enough. Also trusting that the meter stick, I could have used this one right here, is accurate. So center of mass, somewhere around there to the center of the pivot point. Let's see, that thing is going to, and it's swinging some there. I'm going to the center of the bar, so that is, it's like 78.7. And we need to find the period. So what I'm gonna do is I can pull it back a little bit, let go. I do need some people timing. So when we're ready, I'm gonna pull it back and go 3, 2, 1, go. When I say go, I'm gonna let go at that point. We're gonna time how long it takes to do 10 full swings. All right. Got timers, all timers ready? Ooh, I should be able to do this too. There we go. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop. Well, mine's that lousy precision, so I might not use it. All right, so what times did people get?
I got 16.07, but I was slightly delayed.
16.07.
Yeah, but I was slightly delayed by maybe like half a second.
17.17.
17.64.
Anyone else? I have 17.5, but I don't have the level of precision that the others do, so I'm gonna throw mine out. All right, so that's the time for 10 swings. What's my average here?
So I think that's 17.135.
125?
135.
135. Yeah, that's it. All right. So that's for 10 swings, and so my period is 1.7135 seconds. Divide by 10. Now we come over here to my formula. And so 1.7135 equals the square root of, did I erase it? I did. Let's see if I can see it. It's like, there we go. 0.787 meters divided by, that's seconds over there, G. So G will be 0.787 meters.
Oh, you're trying to do, time, which is 2 pi L divided by G, right?
Yeah, I forgot my 2 pi
You're good.
there.
You're good.
1.7135, there we go, all right. It's gonna be equal to 4 pi squared times 0.787 divided by 1.7135 squared. Please come up close. And I think you'll see 9.798, we nailed it. Go. What are we getting? I did one, it was a different acceleration due to gravity thing we did in class, and ended up having the acceleration due to gravity over in the Career Center as somewhere around 24, 25 meters per second squared. There are some flaws in the timing.
I got .158,
0.158?
.1158.
Yeah, did you multiply times the 4 pi squared?
Yeah.
Yeah, I'm not sure how you got a number that low. So 4 pi squared times 0.798 divided by, oh, you're off. That should be 1.7135.
Okay, so.
The bottom one is 1.7.
That, yeah, that's 1.7, because the 17 was for 10 swings, so the period is just for one swing.
So that should be 10.58.
I got 10.18.
You had 18, she had 5.8. You got 5.8 also? 2 votes for that. Brandon, you exasperated there.
I don't know what I'm doing, cause I got
I got 0.58.
18.13.
Huh. Did you square the pi? No, that wouldn't have explained. You had 18. Did you square the denominator?
Oh, that, okay, no.
Okay. And I think what they're saying is that you made a mistake.
Somewhere, yeah.
Or they're conspiring to gaslight you. Yeah, I got some nods over there.
Alright, I see how it is.
Not as dynamic as I was, but I was hoping for much better results. Let's find out what the time actually should have been, given our value, once Brandon comes up.
I got the,
1.7807.
Oh, I got the same number now.
You got the, all right, so you got the 5.8 also, Brandon?
yeah.
All right. So that 1.8 stuff was just mathematical Tourette's, just sort of throwing numbers out. All right, so let's figure out, we had those 4 times right there with that error race, but let's see who actually has the best sense of time in this particular case.
1.7807.
1.7, that's, oh, you already calculated?
Yeah.
1.7807, so for 10 swings, 17.807. So that would have been the 17.66. Who's taking the bow on that one?
There was no 7.66, but there was 16.66.
It's 17.66 written down here. There's 16.07, 17, 17, 1766, and 1764. Did I miss right, Doc?
I think so.
I didn't do it, but I'll blame him.
All right, way to go, Brandon.
Sold.
So it's possible we would have been even more off. Huh. I think whatever we're saying here is that 1607, something was wrong there. That was you, Craig, right?
Nope,
No,
but you
that's
claimed
Ian.
it.
Ian.
But he claimed it.
Yeah, my watch froze.
He said it froze, he claimed it.
Turns out that's my guess, I guess, because, my dad was 17.
Okay,
I
17.66.
wrote it down.
There's that moment whenever I do these experiments where I'm going, this one's gonna work, this is the one.
This is the one.
Past performance is not necessarily an indication of what's always gonna happen. Recognize the power of this, and so let's throw in some of the issues. One, not all the mass, I've talked about the mass bit already. I measured to this, tried to measure to the center of this, and this actually slipped some, so there was a little bit of loss there. But it was swinging sometimes from this spot, and sometimes the rope would slip a little bit. So right now it seems the pivot point seems to be here and not here. Now, does that make a significant difference? No, not really. But we're within 10% of the correct value. You were getting sleepy. All right, so I'm seeing which topics I skipped. So we did simple pendulum, did all that stuff. We did all that. We've not done that.
Questions on the supplemental before I erase?
Let's take a break. Stretch legs. I'm gonna do something radical here. I'm gonna pause the video just so there's not, footage of an empty board here. Would someone please remind me to start this up again? It's flashing, all right. Let's just start out with a series of just absolutely incredible drawings. And then you'll be able to see, if you don't quite have an image of what I'm drawing, then a little bit you'll see better, I hope. All right, so I have some object sitting right here. It's going to give off a sound wave. And that sound wave is just going to start expanding. So imagine you got a very still lake or pond and you throw a rock into it and you get the ripples coming out, or ripple. So at some time later, so this is, the object is not moved, this is just kind of like a comic strip where it expresses different moments in time. That sound wave that was created right here is now expanded out to there. It's supposed to be centered around that dot. And at this point it gives off another sound wave. So at some moment in time later, just before it starts to give out the next one, that first wave has now expanded. And that second wave is now out to there. These are supposed to be circles. And then sometime later, whatever it creates at this moment in time will then be this big, this will be that big, and this will be even bigger. So this is supposed to be expressing just an object giving out sound with some regular frequency. Now, the object's going to move. So it gives out that sound wave. That sound wave that is produced is centered where, basically from the point of production. So that circle should be centered basically where the object was. But now my object is moving off to the right. So the object is now here when that sound wave is there. It gives off a sound wave at this point, so this green wave right here is going to still be expanding, centered about the point at which it was produced. But the second wave, this blue wave here, is going to be centered at this spot right here. And the object's still moving, and so the object's, say, here now. So these circles are representing sort of the peaks of the wave, high pressure, if we're dealing with sound. And so if you were standing over here, you'd be hit by the first pressure wave and then the second pressure wave pretty rapidly, one right after the other. So if you are over here, you're going to be hit with, you'll be hit with the pressure waves faster than you would have had you been here. The wording was off there. Let's try that one again. You'll be hit by the pressure waves more frequently than you would if you had been in the first situation. And if you were standing on the other side, you're going to be hit by the pressure waves less frequently. Now I use the word frequently, that translates very nicely into frequency. You're going to be hit more frequently, so this is a higher frequency. Less frequently, lower frequency. So as the object is approaching you, you get the higher frequency, so it goes away, it's the lower frequency. And that's why if you're standing on the side of the road, you hear the car goes, and it's the higher frequency to start with as it comes towards you, it drops to a lower frequency when it's going away from you. or in the case of a Prius. The fact that you're perceiving something different here, and I guess I do need to throw this in. I use the frequency of the sound and the term pitch interchangeably. I think for the purists, they aren't. Technically, the sound wave has a higher frequency, so we hear a higher pitch. But I do use the pitch and frequency interchangeably. Actually, I rarely use pitch at all. But if you're a purist out there and you're thinking you should be saying pitch, probably. But I'm not going to. All right. So the fact that you are getting a higher frequency here than here because of the movement of the object, this is known as the Doppler shift. I believe named after Doppler. Just taking a stab at that one. We can also have a Doppler shift even without the source moving. It could be that you're moving. So if you are over here and you are running towards the source, you're going to run into these waves with a higher frequency than if you were running away from it. So as you run towards the source, you also hear a higher frequency. And so as long as the two objects are coming towards each other, higher frequency, going away from each other, relatively speaking, a lower frequency. Or if you're standing just still, it's whatever. You know, you have the same frequency. The frequency that's emitted and the frequency received is the same. Now let's take a look at it when this is done professionally. Questions before I cover part of this up? Now let's find out if YouTube will catch the copyright violation. Something might be happening, I'm not sure.